Good morning, AST301. I'm Nolan Richardson. My topic choice is one that likely many of you are familiar with, and that is the discovery of planets beyond our own solar system, and the Nobel Prize in Physics for the discovery of an exoplanet orbiting a sun-like star, which in 2019 was awarded to Didier Queloz and Mitchell Mayer. Now, contrary to what the title of that Nobel Prize is, the first exoplanet wasn't discovered by Queloz and Mayer. In 1992, two radio astronomers, Alexander Wolszczan and Dale Frail, discovered an anomaly around pulsar 125712, which would later be described as the first confirmation of an exoplanet. However, these two bodies were likely the burnt-up cores of planets that were unlikely to have formed around the pulsar in its current state. 3 years later, in 1995, Didier Queloz and Mitchell Mayer confirmed a single planet, a hot Jupiter, using the radial velocity method on 51 Pegasi, a main sequence G-type star 50 light-years from Earth. The discovery was a remarkable spark which kicked off the hunt for exoplanets, and it only took 24 years for them to receive a Nobel Prize. The search for exoplanets is the search for our place in the universe. Giordano Bruno is likely the most famous case of asking what we are amongst the stars, though he's likely not the first to wonder if we're alone. It took nearly 3 centuries for Bruno's silence at the stake to be answered. In 1984, scientists discovered the first evidence of planets around a distant star, an accretion disk that was likely the site of planet formation. In 1992, the pulsar discovery was made of the 2 planets. In 1995, Queloz and Mayer made their discovery around the G-type star 51 Pegasi. In 1999, the first exoplanet was observed via the transit method. In 2001, we discovered the first exoplanet in the habitable zone, not too far, not too close to support liquid water. In 2005, the first direct image of an exoplanet was taken. In 2015, nearly 20 years after Queloz and Mayer's discovery, we had confirmed 1,000 exoplanets. To this date, we've confirmed over 5,200 exoplanets, a 5-fold increase in only 7 years. The methodology for finding planets has evolved as our techniques and our technology have improved. Pulsar timing was the first method to find those planetary cores back in 1992. This involves measuring the very precise pulses emitted by a pulsar, predictable and more accurate than any clock that we could make. A disruption to these pulses was the first sign that there was an outside influence acting on the pulsar. The next method, gravitational microlensing, or the brightening of a background star as a massive object passes in front of it, is another such method. This is an extreme example. This is in the picture a galaxy behind a galaxy cluster or a supermassive galaxy being warped and focused due to that massive galaxy's gravity. Similarly, when a nearby star passes in between us and a further star, the luminosity, the brightness of that further star is amplified. And when that star passes, a planet may pass as well, which also increases the luminosity, only slightly, depending on the mass of the planet, but it's still something that's detectable and can be used to confirm exoplanets. The next method, Doppler, or radial velocity. We observe stars, and when we see a planet around the star, we know that that planet is tugging gravitationally on the star, and when that star is tugged towards us, the light from the star is blue shifted, and when that planet tugs the star away from us, the light is red shifted. So we're able to measure the wavelength of this red shift and blue shift. The next method, direct imaging. This is a picture of a direct image that James Webb took. I think direct imaging is the most exciting method of finding an exoplanet, and hopefully James Webb is able to fulfill its mission of mapping a planet's atmosphere around a distant star. But this is a less used method just due to the sensitivity of our instruments. But it's a method that, unlike the other methods, it doesn't require the planet to be within the same celestial plane as our field of view. So gravitational microlensing Doppler transit, if the star is perpendicular, its orbit and its plane of orbit are perpendicular to our line of sight, we're not going to see it. The last method is the transit method. So this is the most impactful method up to date. The transit method is one in which the brightness of a star decreases as a planet passes in front of it. This has led to a majority of exoplanet conformations on the Kepler spacecraft, which peers into a small area of the sky. I posted the related equations here that I've gotten from the book as well. Most of these observations, not all of them, are done by observing light and observing the wavelength of light, especially when you look at the Doppler method. You're looking at changes in wavelength, and so that relationship between wavelength, frequency, and the speed of light is super important to how redshifted or blue shifted the star is. The next equation, the luminosity equation. The luminosity equation is definitely important for gravitational microlensing and important for direct imaging. We also see it used during the transit method, and all of these are very precise measurements that we're taking. And the last image posted here is the inverse square law, which, as you know, as the distance to a star increases, its luminosity decreases by a square factor, or its brightness rather. So final thoughts. As we peer further and further into the night sky, our questions grow deeper. How did we get here? What are we? Are we alone? Finding planets riding around distant stars is crucial. It gives us a story of a past that we weren't around to see. It gives us hope that one day we'll have a new place to call home. In this moment, it teaches us that we belong, that we aren't some loner in a universe too vast to comprehend. It gives us the tools to predict how common not only Earth is, but life as well. It gives us the tools to expand our model, to heighten our understanding, and to become a shepherd of the stars. Thank you for your time.